All right, so the next thing that I wanted to talk about is this idea of eating for your blood type, which I know is quite popular, but I have never seen a real explanation as to why eating for your blood type should actually work. There is some people talk about lectins in food and how they stick to certain these proteins under the red blood cells, and they've done large studies that have really proven that this is really not the case, and that for the most part the lectins are things that are present in things like beans, and if you soak them overnight, which I always soak my beans, then it'll save you some gas, and it should not mess with your ABO antigens on your red blood cells. Next. However, the idea of eating for your blood type is a huge idea, and a lot of people are after it because, well, you've got a hole, you got to fill it, and this fills it because you got this problems because you're eating the wrong thing. All right, so now here I wanted to talk a little bit about antibiotic resistance. As I just said, I am an antibiotic overprescriber, admittedly. 75% of all the antibiotics in America today are not prescribed by doctors. And they're not used on humans. They're used on animals in feedlots because we give them growth hormones so we can get more milk out of their breasts. They cracks the breasts. All the cows get mastitis, and so we prophylax against that mastitis by giving them antibiotics. And also, I should just say there is this principle of pharmacology about resistance. And resistance does not happen as a result of someone taking high-dose antibiotics to treat infection once, maybe not twice. If you keep doing it, yes, they will. Yes.
How do you think of MRSA?
How do I think of it? I'll talk about it in a minute.
Good, okay. That just seems like one of the good ideas.
And so, when we go with low dose, long-term antibiotic treatment, that's when we develop resistance. This is one of the proven principles of pharmacology. And low-dose antibiotics are all around us in the food that we eat, but they're also, to a great extent, we are destroying a lot of bacteria by using detergents. And detergent use is actually associated, and soap use is associated with MRSA. Next, please. I think I must have had my slides just a little bit out of order, but back at about 22 years ago in San Francisco, nobody got MRSA, except for people who were on kidney dialysis, who were in the hospital all the time, so chronic patients. And the only people in the community that harbored any MRSA were Samoans. Something about the waters in Samoa, somehow. But we saw a lot of Samoans at San Francisco General, and a lot of them would culture positive for MRSA, and nobody else would at that time. That has changed significantly. Now a lot of healthcare providers and a lot of people in the community carry MRSA in their nose. And there's been significant association with the use of certain detergents. And also, if you have someone in your family who has MRSA, someone you're living with, you will get MRSA pretty quickly from them as well. But another source of antibiotic resistance in America today are GMOs. GMOs are made by genetically modified organisms are made by introducing a foreign gene into a species and then propagating that species. Well, whenever you do something, it's not 100% effective. Even if you're really, really good at most things, you took a test and you got a 98% on it, that's damn good. But if you're selling seeds, you really don't want to sell seeds that are 98% pure. You're going to be like, you know what, 2% of your yield is gone. You really want to have 100% accuracy. And usually the gene transfer efficiency is not 98%, it's more like 80, 85, 90%. So you really can't be selling seeds that are 20, 15% defunct compared to what you're trying to represent. Nobody wants to plant a crop and have it be only 85% good. So what they do, along with that foreign gene that they're introducing into the seed, they introduce an antibiotic resistance gene. The antibiotic resistance gene has the role that if it is incorporated into the DNA of the target species, then what you do is you culture that on a dish which contains that antibiotic. All the cells that didn't take the genes will die as a result of interacting with that antibiotic. The cells that got the gene, so when the transfer of the gene worked, the antibiotic resistance gene also came, and all of a sudden, those cells lived. So you took 85% of your sample that was good, and they lived, and you killed off all the other cells that didn't have that gene. So what happens then subsequently when you go and introduce this gene into the environment? Well, that gene is transferred to other species, other weeds around there, and also the bacteria in the soil. And the problem isn't always that. The problem isn't that now all of a sudden you've got all these weeds that have some antibiotic resistance genes. The problem really is that once you wake up those cells that now have this antibiotic gene, they realize, there are antibiotics around. Here's danger, here's a problem. Let's start making plasmids of not just the gene that just came in, but all the other dormant genes that we have that are antibiotic resistance genes, so that we can fight off whatever else is out there. Now somebody's is attacking us, somebody's telling us, hey, there's a problem. It's kind of like somebody came and robbed your car. You're probably going to be a little more careful about your house. The same thing with these organisms. Once you start bringing in antibiotic resistance genes, once you start dousing them with things like Roundup, they start waking up the other genes that are in these plants. Next one.